All right, this is part 3 of the trigonometric integral example problems. And so, okay, this first problem here, now we've got a cotangent. So we were working with, before we were working with sine, combinations of sines and cosines, and then also combinations of tangents and secants. And now we have a cotangent. And so what we're going to do here is it's the exact same idea as what we were doing with sines and cosines and tangents and secants, but we're going to use the trig identity 1 plus cotangent squared of x is equal to cosecant squared of x, and then just take a look at what the derivatives of cosecant and cotangent are. And so the derivative of cotangent x is minus cosecant squared of x, and then the derivative of cosecant x is minus cosecant cotangent x. So it's similar to what we do with tangents and secants. Okay, so here we don't have a combination of cotangents and cosecants, and we have a cotangent squared, but the derivative that results in something squared is the derivative of cotangent x is cosecant squared x. And so what I mean by that is, if this was the integral, the definite integral of some like cosecant squared, like minus cosecant squared, just cosecant squared, well then we're done. We've got that integral right here. So we would rather, from an integral standpoint, we'd rather be working with, in this situation, we'd rather be working with a cosecant squared. So let's convert this to cosecant squared of x minus 1. Okay, so this is right, but the difference is we can get this integral easily, because we know that the derivative of cotangent x is minus cosecant squared of x. So this is just minus cotangent x. Okay, and then this is just x. All right, so minus cotangent pi over 2 minus cotangent pi over 6 minus pi over 2 minus pi over 6. Okay, cotangent is 1 over tangent. Let's just put these into our calculator. So, okay, cotangent pi over 2 is 0. Okay. All right. Plus cotangent pi over 6. Root 3. Okay. Minus, all right, 3 pi minus pi is 2 pi, so 2 pi over 6, which is pi over 3. All right, so root 3 minus pi over 3. Okay. So now we've got a combination of cotangents and cosecants. We've got 1 plus cotangent squared is equal to cosecant squared. And then, all right, so what's the parallel here between the tangent secant method? All right, so we don't have an even cosecant squared. We don't have an even power on the cosecant. So to me, this is going to be, we're going to be using this. So we're going to want to separate out a cosecant cotangent. So let's do that. Okay. So cotangent to the fourth and then like that. And then so then we want to we're going to be making the substitution that u is equal to cosecant of psi. So that means we want to make this term here a function of just cosecant. Therefore, this cotangent to the fourth will substitute for, so cosecant squared minus 1 squared. Oh wait, this has a d psi. Okay. So, all right. So now what we can do is we say u is equal to cosecant psi, and therefore du is equal to minus cosecant psi cotangent psi. And so we'll put the minus here. Okay, so there you go. So that, d psi. So there you go. We can substitute here, and therefore, and also let's update the limits of integration. That usually makes it a lot easier. So when u is equal to, or when psi is equal to pi over 4, what does u equal to? All right. Cosecant pi over 4 root 2. Okay. And then when psi is equal to pi over 2, u is equal to 1. Okay, so now we've got u squared minus 1 squared, u squared, and then du, but we put a minus sign. So we've got u to the fourth minus 2u squared plus 1 u squared du. Okay, u to the sixth minus 2u to the fourth plus u squared du. Okay, so 1/7 u to the seventh minus 2/5 u to the fifth plus 1/3 u cubed evaluated from root 2 to 1. All right, so, okay, let's save room here. Plugging in 1/7 minus 2/5 plus 1/3 minus 1/7 2 to the 1/2 to the 7th, so 7/2 minus 2/5, and then 2 to the 5/2 plus 1/3, and then 2 to the 3/2. Okay, so 1/7 minus 2/5 plus 1/3. Okay, 1/7 times 2 to the 7/2 minus 2/5 times 2 to the 5/2 plus 1/3 times 2 . So 8/105 minus 22/105 root 2. 22 root 2 over 105. So 8 minus 22 root 2 over 105, which is approximately equal to okay, but there was I forgot to bring this minus sign. So it's going to be, okay. You have a minus sign up front, so this would be 22 root 2 minus 8 over 105. Approximately equal to minus, or it would be, so this is times minus 1.22. But this is the exact answer. Okay. So, this is one that you could, that might be in a table of integrals, but they want us to evaluate this. And, you could try integration by parts, but I tried integration by parts, and sometimes, like, I think it was, functions like the natural log of x, for example. If you can find the integral of the natural log of x using integration by parts, where you make u is equal to the natural log of x and dv is equal to dx. And so you would think that might work here, but it ends up not working. And so to solve this, what we want to do is we want to find a clever way of creating a form where we can make one of those trig substitutions. So it's going to be, we're working with cotangent and cosecant, right? Because the derivative of cosecant is minus cosecant x cotangent x. And then the derivative of cotangent is minus cosecant. So the idea is, like, all right, if we multiply this by 1 in the form of cosecant x over cosecant x, then we would get 1 over cosecant x, cosecant squared x dx. And so potentially we could say that u is equal to cotangent x, so that du is equal to cosecant squared x dx, but we don't have a cotangent x here. Okay? So what we're going to do is we're going to multiply by 1 in the form of cosecant x plus cotangent x over cosecant x plus cotangent x. And this is going to end up putting it into a form where we can make the substitution work. So okay, so now what do we get? We get cosecant squared x, and that's part of this, that we have a cosecant squared plus cosecant x cotangent x over cosecant x plus cotangent x dx. Okay, then now the main trig identity is 1 plus cotangent squared of x is equal to cosecant squared of x. Okay, now if we say that u is equal to cosecant x plus cotangent x, then du is equal to minus cosecant x cotangent x minus cosecant squared of x. And therefore minus du is equal to cosecant squared of x plus cosecant x cotangent x, right? So the substitution is going to work perfectly. So we've got 1 over u du with a minus sign up front. So this is minus natural log of the absolute value of u. And we can bring this minus sign like that, okay, plus c. Okay, for these types of trigonometric integrals, we use these trig identities. Okay, so we can write this integral as, this is sine of something times cosine of something. So 1/2 sine of x plus y, so sine of 13x plus sine of 3x. Right? Sine of x plus y plus sine of x minus y. And you know, this is a good illustration of when it comes to integrals, you know, up to this point, you typically, a lot of times you want to go in the other direction. You would rather have a form like this. This is cleaner, right? This is messier. But when it comes to integrals, having like a sine of 13x or a sine of 3x, that's easy to work with for integrals. Okay, so we've got 1/2 Okay, so the integral of sine of 13x is minus 1 over 13 cosine of 13x. And then the integral of sine of 3x is minus 1 over 3 sine 3x. Plus c. Okay, so same type of process. Let's reference these trig identities. Here we've got cosine of something times cosine of something. So we've got 1/2 cosine of this minus this. So cosine of minus 5t, and I think that's going to be cosine of 5t. I think cosine is an even function, right? So cosine of minus 5 times t is just cosine of 5t. So yeah, cosine of 5t plus cosine of 5t plus 10t, so 15t. Okay, so we've got 1/2, and the integral from 0 to pi over 2. Okay. So the integral of cosine 5t is 1/5 sine of 5t. And the integral of cosine 15t is 1/15 sine of 15t. Okay, and we want to evaluate this from 0 to pi over 2. Okay, so when t is equal to 0, this whole expression goes to 0. So we just need to evaluate this at t is equal to pi over 2. Okay, so sine (5 pi over 2) is 1, and then sine of 15 pi over 2 is -1. So 1/5 minus 1/15 is, well, we can do this. So that's going to be 3/15 minus 1/15. 1/15. Okay, so I see this 1 plus cosine 2x, and I think of the half angle identity, which is cosine squared of x is equal to 1/2 1 plus cosine 2x. Okay, so let's see if we can use this. Let's see where this gets us. So if we write this as, so 2 like that, then we can say this is 2 cosine squared x. Okay? So this is root 2 like that. So okay, so this is the integral of cosine x is sine x. Sine of 0 is 0, so root 2 sine pi over 6. Sine of pi over 6 is 1/2. So root 2 over 2. Okay, so this doesn't take on one of the forms that we learned in the textbook, like a power of tangent and a power of secant multiplied by each other, but we're going to use the exact same concepts to solve this. So we'll use secant squared x is equal to 1 plus tangent squared x. And so, okay, so if we could have 1 minus tangent squared x over 1 plus tangent squared x, I'm not sure if that would be helpful. But, okay, so let's just play with this a little bit. So 1 minus, and then tangent squared x is secant squared x minus 1. So that would be what? If we got secant squared x minus 1, then that's going to be 1 plus 1, so it would be 2 minus secant squared x. 2 minus secant squared x over secant squared x. And okay, so we could divide. We could do this. I wonder what this is going to do. So 2 over secant squared x dx minus the integral just dx. Okay. And so this is 2 integral of, the inverse of secant is cosine. So cosine squared x dx. And we know how to solve cosine of x to any power. We use, so okay, let's write this out. We use the half angle identity. Okay, cosine squared of x is 1/2, 1 plus cosine 2x. So okay, and this is just x. So we've got, this is going to be the integral of dx plus the integral of cosine 2x dx. So this is x, and then 1/2 sine of 2x. So sine of 2x over 2 plus c. Okay. So, I'm thinking integration by parts, but we'd rather have the secant squared because that's easier to integrate. So secant squared of x is equal to 1 plus tangent squared of x. So okay. Right, so we've made this more complicated. Like this hasn't, we have x secant squared x dx, and now we have to evaluate this additional integral. But the idea is this is easier to work with in terms of integration by parts, because we can say, okay, u is equal to x, so du is equal to dx, and then dv is equal to secant squared x dx. Therefore, v is equal to tangent x. That's really clean. And so this should result in an integral that's easier to, a new integral that we can evaluate. So x secant squared x dx, u times v minus the integral of v du. Yeah. So x tangent x minus the integral of tangent x. The textbook gives this to us, natural log of the absolute value of secant x. So, okay. This is x tangent x minus natural log of the absolute value of secant x, and then minus this integral, which is 1/2 x squared. And that's it, plus c.